Hey everyone, Mr. Hauk here. In today's video, we're going to introduce the concept of the limit. So the limit is fundamental to the study of calculus, and it's important to acquire a good working knowledge of the limit before moving forward, because you'll find out through the duration of this course that really it's all about limits. When we start to investigate derivatives and integrals, you're going to see that they're defined using limits. So we need to really have a good grasp on limits. So let's investigate this concept of limit. And we're going to use our calculator to generate a graph of f of x equals x squared minus 4 over x minus 2, where x does not equal 2. Now the first thing we want to ask ourselves is, why is x not allowed to equal 2? And it's really quite simple. We can see that if x is equal to 2, so let's say that we replaced these x's with 2's, well, putting a 2 in for x in the denominator would give you 0, and we know that we can't divide by 0. So if this turns into a 0, we are undefined at x equals 2. So in writing, f of 2 is undefined because the denominator equals 0 at x equals 2. Okay, so that's why x is not allowed to equal 2. When you get 0 in the denominator, the function would be undefined. Okay, and what we want to do though, since we know that this function is undefined at 2, we want to understand what's happening as this function gets really, really close to 2. So we already know that at 2, the function is undefined. Okay, but what happens as we get really close to 2 as we approach 2 from the left, and what happens as we get really close to 2 as we approach 2 from the right? We're talking about the x's, of course. What happens as x approaches 2 from the left, and what happens as x approaches 2 from the right? But first, let's take a look at the graph of this. Okay, so I'm going to use a graphing calculator called Desmos. You can use your TI-84 to graph it just fine as well, but let's look at the graph in Desmos real quick. So right here, I've got it graphed. We have x squared minus 4 over x minus 2. And notice that, as we close in on 2, at 2, we can see that the value is undefined, and we already know why, because we plug it 2 in the denominator. Denominator 0, we can't have that in the denominator. But let's see what's happening as we get really, really close to 2. So as the x values approach 2 from the left, the y values are getting really, really close to 4. And as the x values approach 2 from the right side, the y values are also getting really, really close to 4. And let's see that in the form of a table here. So if I approach 2 from the left side, we want to look at x values that are getting closer and closer to 2 from the left. So if I plugged in 1.5 into this function, x squared minus 4 over x minus 2, the value that we would get is 3.5. If I plugged in x equals 1.75 into here, we would get 3.75 for the function value. If I plugged in 1.9, we would get 3.9. If I plugged in 1.99, we would get 3.99. And if we plugged in 1.999, we would get 3.999. So notice that the closer the x values from the left, the closer we approach to 2 from the left, the closer the y values are getting to 4. Well, let's do that from the right as well. Let's take x values to the right of 2, and let's watch what happens as x approaches 2 from the right side. So if I plug in a 2.5 into this function, well, plug in 2.5, you'd get 4.5. If we plugged in 2.25, we would get 4.25. If we plug in 2.1, we'd get 4.1. 2.01 would give us 4.01. And if we plugged in 2.001, we would get 4.001. So we can see that as the x values that we're plugging in approach 2 from the right side, we see the y values are starting to approach 4 from the right side. And notice that from the left and the right, in this example, the y values are approaching 4 from both sides. And that's what we saw here in this graph. As we approach the x value of 2 from the left, we see the y values getting really close to 4. As we approach the x value of 2 from the right, we see the y values getting really close to 4. And that kind of explains this concept of limit. So let's talk about the informal definition of a limit. if the y value of a function f of x becomes close to a single value L as x gets closer and closer to a point C from both the left and the right side, then the limit of f of x as x approaches C is equal to L, which in mathematical notation is this right here. So this is saying the limit of f of x as x values approach C equals L. L would be what we call the limit. Okay? So let's apply this definition to this function that we just observed as x is approaching 2 from the left and right. So the limit of the function f of x as x approaches 2, well, we can see that as x approaches 2 from the left and the right, the limit is going to be 4 because that's the y values or the function values that you're approaching. So we would say that, and let's write this out here, the limit as x approaches 2 of f of x is equal to 4. Okay, now this is an informal definition of a limit. There is actually a much more rigorous mathematical definition of a limit called the epsilon delta definition. And if those of y'all go on to take some more advanced math classes in college, such as analysis, you will use the epsilon delta definition rather than this informal definition of a limit. If you want to investigate that further, check out this link or this QR code, and it'll take you to a page where you can explore the epsilon delta definition. Okay? But let's continue on with our concept of the limit. So in this next example, we want to graph the function y equals g of x, where g is defined by this step function. We call this a step function, and you'll see why here in just a moment. So this is a step function. Okay, and the way that this step function works is that, let me grab a different color here. Let's grab blue. So here's what it's saying. It's saying that if x is not equal to 2, then the function value is always going to be 1. But if x is equal to 2, then the function value is going to be 0. So let's go to x equals 2, and let's plot our point at the function value of 0. So that'd be right here. This is our x value of 2, and we can see that our y value is 0. Okay? But everywhere else, except for at 2, the y value is going to be 1. So everywhere else, the y value is 1. So like if I went to the x value of 4, well, we can see the y value is right here at 1. If I went to the x value of negative 3 right here, I can see that the y value is at 1. The only place the y value is not at 1, or the function value in this case, is when x is equal to. When x is equal to 2, we have this little closed-in filled circle here at 0. Okay, we call this a step function. So let's calculate some limits real quick. Let's think about what the limit of this function g is as x approaches 2. Now let's go back to our definition, our informal definition of a limit. The y value of a function f of x becomes close to a single value L as x gets closer and closer to a point C from both the left and right side. Well, the point C that we're getting closer and closer to is 2. So as we get closer and closer to 2, so let's trace our function. As we get closer and closer to 2, from the left and the right side of 2, the function values are approaching 1. So that would be our limit. So the limit of g of x as x approaches 2 is going to equal to 1, because on the left and the right of 2, the function values or the y values are getting really, really close to 1. Okay? But exactly at 2, so the function value at 2, that's what this says right here. What is the function value at exactly 2? Well, exactly at 2, the function value is 0. Okay? So that shows the difference between what a limit is versus a function value. A limit, you're concerned with what are the function values approaching on the left and right as you approach this certain x value. But we don't actually care what the function value is exactly at that point. Okay? So a limit, we're looking what's happening to the function values around that point as you approach it, not so much what's happening exactly at that point. Now, that can be a little confusing, especially at first. If this is your first time seeing limits, that can be a little confusing. But think of it as a broken bridge. okay? Even though the bridge is broken, it seems like the missing section, maybe it's fallen in the water. You can tell where the missing section should be. So the height of that point would be the value of the limit. Limits are important because they give us the ability to discuss what is going on at a point mathematically, whether the bridge or graph, in this case, exists at that point or not. So with limits, we are only concerned with the y value the graph approaches, not what the y value actually is at that point. I'm going to highlight that because that's extremely important. Okay, again, with limits, you're concerned with the y value the graph approaches, not what the y value actually is at that point. All right. So that brings into discussion the concept of one-sided limits. So take, for example, this graph right here. And suppose we have the graph below. Notice that the function below does not approach the same y value as x approaches c from the left and the right sides. So here's c. Here's c on my x-axis. And notice that, if I trace the graph on the left side of c, the y values to the left of c are approaching this y value of k. But if I approach c from the right side, so I start tracing the function on the right side of c, the y values are approaching L, okay? So we call k the left-sided limit as x approaches c, and we call L here the right-sided limit as x approaches c. And we can distinguish between the left and the right side limits separately. So sometimes we're only interested in what's happening as the x values are approaching from the left or the right, okay? And here's the notation that we would use. So we say that the limit of f of x as x approaches c from the left equals k. We use this notation right here. Notice this little minus sign here in the exponent. This minus sign means you're approaching this c value on the x-axis. The minus sign means you're approaching from the left. If you put a plus sign here in the exponent, that means that we're approaching c, or approaching that x value from the right side. Okay, so if you see the minus sign up here, we're talking about a left-sided limit. If we see a plus sign up here, we're talking about a right-sided limit. Okay, now for a limit to exist, I'm going to highlight this as well. This is an important theorem here. For a limit to exist, the left-sided limit and the right-sided limit must be equal to each other. The left-sided limit and the right-sided limit must equal the same value for a limit to exist. Okay? So let's investigate a little more closely with example 3 here. So here in example 3, first we want to get an idea of what this looks like visually. We have this piecewise defined function, and let me get a couple of different colors here. I'm going to use green to represent this part of the piecewise function. I'm going to use blue to represent this part of the piecewise function, okay? And let's tackle this part first. So if the x values are bigger than 2, the function is modeled by 5 minus 2x. Well, let's graph 5 minus 2x real quick. This is just a linear function. The y-intercept is 5, so let's put a point at 5. 1, 2, 3, 4, 5. We can see the slope is negative 2 over 1. So we would go down to right 1, down to right 1, get a bunch of points, right? We've done this in algebra. So this is what, if I connected this with a line, that's what 5 minus 2x would look like. But we only want it to look like 5 minus 2x when x is exclusively bigger than 2. So here's 2 on the x-axis. I don't want any of the points from when x is less than 2. And when it's at 2, it's actually not defined here. Notice it says x is bigger than 2 exclusively. So I'm going to go ahead and even erase the point at x is at exactly 2, and I'm going to put an open circle here. Okay, it actually should be right there. Okay, so here is that part of our piecewise defined function. Now let's look at the bottom part. I'm going to show that in blue just to kind of make it stand out from the top part. So if x is less than or equal to 2, the function looks like this, x minus 3. We can see that the y-intercept is negative 3. Let's put a point there. And we can see the slope, 1 over 1. That's the coefficient of x. So up 1, right 1, up 1, right 1. or opposite, down one, right, down one, left one, down one, left one. And notice that this is anytime x is less than or equal to 2, so I don't want to continue this graph greater than 2. So we'll stop right there. And graph. Now notice on my graph, again, that we follow the green function right here when x is greater than 2, and we follow the blue function when x is less than or equal to 2. I have a closed circle here at x is equal to 2 on the blue part because this is less than or equal to. So at exactly equal to 2, the function follows x minus 3. 5 minus 2x is not defined at 2. It's defined when we're greater than 2. Okay, so that's why we have this open circle right here. All right, so now let's use this graph to try to identify these limits or these pieces here. So graph the function. We have already done that. I'll go ahead and check that off. Let's find the limit of f of x as x approaches 2 from the left side. So here, and I'm going to put this in red, here's our x's. There's 2 on the x-axis. If I approach 2 from the left side, so if I take the left side of 2 and I start tracing the function and start having the x values approach 2 from the left, like this. So we're approaching, imagine there's like a wall right here where 2 is. Okay, if I start approaching 2 from the left, the y values are getting really, really close to -1. So that would be our left-sided limit. Okay, the limit of f of x as x approaches 2 from the left is equal to -1. Let's look at the right-sided limit. The limit of f of x as x approaches 2 from the right side. Well now, again, imagine there's like this wall at x is equal to 2. If I approach that wall from the right side, so I'm tracing the function on the right side of it, the y values are getting really, really close to +1. So the right-sided limit as x approaches 2 is equal to +1. So now that begs the question, well, if the left-sided limit, if we're looking at the limit as x approaches 2 from the left is -1, and the limit as x approaches 2 from the right is +1, then what's the limit as x approaches 2? Considering, looking at both sides at the same time. Well, we're going to go ahead and say that that limit does not exist, DNE. And the reason why it doesn't exist is, remember the limit existence theorem. A limit exists only if the left side and the right side limits are equal to each other. Well, the left-sided limit, as we approach 2 from the left, is equal to -1. But as we approach 2 from the right, the limit is +1. So this limit does not exist because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. Okay? Last little piece we want to look at here is the function value at 2. So when you see this means the function value exactly at 2. I'm not looking to the left or right of it. We're not calculating a limit here. I want to know exactly what's happening at 2. Well, if I look exactly at 2, is it going to be +1 or is it going to be -1? Well, it'd have to be -1 because we use x minus 3, or the blue line that I drew here. This is the one we use when x is less than or equal to 2. So we're going to say that the function value is -1. Okay. So hopefully all this limit stuff is starting to make sense, if it wasn't already. All right. Now, there are times, and you've already seen an example. We saw an example right here with example 3, part D. But there are times when a limit fails to exist, meaning that we are unable to find a limit unable to find a value for the limit at the given point. When this happens, we say that the limit does not exist. I'll use D and E as shorthand notation. So there are 3 types of common function behaviors that lead to a limit not existing. The first one is the one that we just saw. F of x approaches a different number from the right side of C than it does from the left side of C. Very clear right here. We're looking at the x value of 2. Again, imagine like a little barrier here. As we approach 2 from the left side, we see the function values are going to -1, but as we approach x equals 2 on the right side, we can see the function values are going to +1. So the left and the right side are not converging to the same location. That's an example where the limit does not exist. Another example is when f of x increases or decreases without bound as x approaches c. So as your x is approaching a certain value, if your y values or function values are either increasing without bound or decreasing without bound, we would say that the limit does not exist. And you'll see an example of that here momentarily. The third type of a limit that does not exist is when f of x is oscillating between two fixed values as x approaches c. This one is a little, you don't see this one as often. However, let me show you what something like this would look like. Let's say that we have, and this sketch might be a little rough, but hopefully we'll get the idea. Let's say that we're bouncing between +1 and -1. And let's say we have a curve that's doing something like this. Not the greatest graph, but we kind of get the point. Notice that the function values are bouncing between -1 and +1. So, and it's the oscillating behavior is happening right in here. That'd be an example of where you have oscillating behavior. It keeps bouncing between two fixed values as we approach a certain number. We don't really know what's happening in there. It just keeps bouncing back and forth. We would say the limit does not exist. Okay. But let's look at some examples here. So, example 4, let's find the limit of the absolute value of x divided by x as x approaches 0. Now, to get an idea of what this is going to look like, let's go ahead and sketch ourselves a quick little graph, or quick little table rather. And we'll use the table to sketch the graph. So we have our x values, we have our function values, f of x, and we know that we want the x values to approach 0, so we want to know what's happening to the left and the right of 0. So I'm going to put 0 dead center of my little table. And let's think about 0 real quick. If I plugged in 0 for x, thinking about what's happening at 0, well, if I plug in 0 for x, you get a 0 in the denominator, which we know would make this undefined. So at 0, we know that we have a hole, okay? Or some kind of jump. It's no matter what, it's not defined there. So let's think about what's happening as we get closer and closer to 0. So, maybe on the left side of 0, let's start looking at things like, maybe -5, -2, -1, -0.1. So notice that we're approaching 0 from the left. And let's do the same thing from the right side. Maybe let's look at +5, +2, +1, +0.1. So the x values are approaching 0 from the right side. So we're closing in on 0 from the left, closing in on 0 from the right for the x values. Let's see what happens to the function values. Well, if I plug in a -5, absolute value of -5 over -5, we know absolute value just turns values positive. This would be 5 over -5, which would be -1. So this would give us -1. If I did this with -2, absolute value of -2 over 2, -2, that'd be 2 over -2, that'd be -1 again. And we could follow that trend. I plug in the -1, we get 1 over -1, that'd be -1. Same thing would happen here. So we can see that anything to the left of 0 on the x-axis is giving a function value or y value of -1. If we look at the right side, so let's plug in, 5 into the function. So absolute value of 5 over 5, that'd just be 5 over 5, which is 1. So it looks like we're getting +1. And that would happen with these values as well. So let's go ahead and graph this here. We can see that as x approaches 0 from the left, all the function values are -1. But we have a hole at 0. It's undefined at 0. And anything to the right of 0, we can see has function values of +1. So that's the kind of graph that we end up seeing. And let's think about what our limit would be as x approaches 0. I'm going to go ahead and say that it does not exist. And the reason that this limit does not exist is because the left-sided limit, as x approaches 0 from the left-sided limit is approaching -1. But the right-sided limit, as x approaches 0 from the right, well, the y values here are approaching +1. So your left side and your right sided limits as x approaches 0 are not equal to each other, so the limit does not exist. And you can see it pretty clearly. Your limit's not going to exist when you have this big jump here. We call this a jump discontinuity. We'll see that later on when we start talking about discontinuity. But yeah, so this limit does not exist because the left and the right side limits do not equal each other as x approaches 0. Okay? Let's look at this one. Investigate this limit. The limit is x approaches 1 of 1 over x minus 1 squared. And we're going to use this table right here to investigate this one. So first things first, we're having x approach 1. I'm going to put that in the middle of my table here. And if I were to plug in 1, well, 1 minus 1 is 0. 0 squared is 0. So I plugged in 1. The whole denominator would turn into 0, which we know is not allowed. That'd be undefined when x is equal to 1. But now let's plug in some other values. Let's let the x values approach 1 from the left, and then let's let the x values approach 1 from the right. If I took 0.5 and I plugged it in here for x, the number that you would get, let me use a different color than blue, let's use green here. The number that you would end up getting is 4. You can check that in your calculator. If I plugged in 0.9 into x, and I evaluated, we would get 100. And if I took 0.999 and plugged in for x, we would actually get 1,000,000. Again, if you don't believe me, plug it in, try it, see what you get. So now let's look at the other side here. Let's start approaching the x value of 1 from the right side. If we plugged in 1.5 for x, we would get 4. If we plugged in 1.1 for x, we would get 100. And if we plugged in 1.001 for x, we would get 1,000,000. So what does this graph look like? Well, to really get an understanding of what the graph looks like, we need to remind ourselves about vertical and horizontal asymptotes. So in something like this, when you have a denominator that can create a problem, right? We saw that if we plugged in +1 right here, if we plug in a +1, it turns the denominator to 0, and that's bad. It gives us an undefined value at 0. That's actually a vertical asymptote that is creating that. So we have a vertical asymptote, and I'm going to abbreviate this with VA. We have a vertical asymptote at x equals 1. So I'm going to go ahead and draw in with a dashed line a vertical asymptote. But we also have a horizontal asymptote. And the rules for horizontal asymptote are a little more in depth. So for horizontal asymptotes, we look at the degree of the numerator versus degree of the denominator. And I'm going to go ahead and write this down. I encourage you to write this down as well. If the degree of the numerator, let's do denominator first. If the degree of the denominator is bigger than the numerator, then you will always have a horizontal asymptote at y equals 0. Okay? Let me actually make that a little clearer. Let's say HA, horizontal asymptote, at y equals 0. If the degree of the numerator and the denominator is the same, so if same degree, by the way, degree, we're talking about the exponent, the largest exponent of the variable. If the same degree for the numerator and denominator, we use the ratio of the leading coefficients. I'll give you an example of that here in a moment. Use ratio of leading coefficients. Okay, let's say just for example's sake that we were trying to find the horizontal asymptote of 3x to the third over 5x to the third. Well, they both have the same degree, right? X to the third over x to the third. Put that back. No. There we go. Yeah, x to the third over x to the third. So we would take the ratio of the leading coefficients, which is 3/5. So we'd have a horizontal asymptote at y equals 3/5. Okay. Now the other case is, we saw if the denominator has a bigger degree, horizontal asymptote at y equals 0. Let me get, there you go, I like this one better. Yeah, horizontal asymptote at y equals 0. Same degree, use the leading coefficients, take the ratio of them, that's going to give you your horizontal asymptote. But if the degree of the numerator is bigger, then you don't have a horizontal asymptote. So if degree of numerator is bigger, no horizontal asymptotes. Okay. So here in our example, we can see that degree 0 on top, a coefficient or a constant rather, 1 is a constant, that's degree 0. But on the bottom, we have this x being raised to the second power. This is degree 2 on the bottom. So the degree of the denominator is bigger than the degree of the numerator, so we have a horizontal asymptote at y equals 0. So let's draw in our horizontal asymptote. Okay, so we have two asymptotes. Vertical asymptote at x equals 1, horizontal asymptote at y equals 0. And let's start to put in our function values here. So if x is 1/2, the function value is at 4. So x is 1/2, y value is 4. If x is 0.9, the y value is 100. Obviously, we can't actually graph that point, and we definitely can't graph this one. We can graph 1.5, 4. So that'd be right here. And now we're just going to follow the asymptotes for a rough sketch. Okay, so that's a rough sketch of what 1 over x minus 1 squared would look like. Now let's actually look at it in a graphing calculator. So right here. And see, we can see that exact behavior. We can see that we have our horizontal asymptote at y equals 0. We can see our vertical asymptote at x equals 1. Okay? So let's figure out what this means in terms of our limit, though. Because remember, our original problem is find this limit if it exists. So find the limit of this function as x approaches 1. Well, here's 1 right here. That's where the vertical asymptote is. And as the function approaches 1 from the left and the right, the y values are blowing up towards positive infinity. We call this increasing without bound. And we just saw right here, if f of x increases or decreases without bound, that means blowing up towards infinity, or decreasing without bound would be going towards negative infinity. If we are increasing or decreasing without bound, as the x gets closer and closer to c, then that limit does not exist. So this limit, d and e, does not exist. That's terrible. I want the, there we go, shaded in a box. Okay. So last example, kind of a culminating example for these notes. I would encourage you at this point in the video to pause this and try this for a minute, and then unpause it and see how the results pan out. Okay. So here we have this graph, pretty crazy looking graph, a lot of stuff going on, a lot of different little pieces. And let's evaluate some limits and some function values. So starting with the limit of f of x as x approaches 0. Notice there's no plus sign or minus sign, so we have to take both into consideration. And the left side limit and the right side limit as x approaches 0 need to equal the same value for the limit to exist. So we're looking at x is equal to 0, and we're looking at what's happening to the y values to the left and the right of 0. So as I trace the graph from the left of 0, and I trace the graph from the right of 0, all the y values are converging towards 6. So the left side and the right side limit as x approaches 0 are both converging towards 6. So the limit of f of x as x approaches 0 is equal to 6. Part B, the limit as x approaches 6 from the left. So now we're having x approach 6 specifically from the left side. So here's positive 6, x is positive 6, and we are approaching 6 from the left side. So I'm looking at my graph, and I'm tracing it as x is getting closer to 6 from the left. And notice the y values are getting closer and closer to 4. So that's our limit. Okay. Part C, the limit as x approaches 2 from the left. So here's the x value of 2, and we want to approach 2 from the left side. So I'm tracing the function, and as we approach 2 from the left side, the function values are getting closer and closer to 0. Okay. Part D, the limit as x approaches negative 6. Notice it's not from the left specifically or the right specifically, so we have to keep both into consideration. Both the left side limit and the right side limit need to equal each other. And if we look at negative 6, here's negative 6 way over here. Well, as we approach negative 6 from the right side, we can see the y values get really close to 0. But we can't approach negative 6 from the left. There's nothing to the left of negative 6. We don't know if it's over here. We don't know if it's over here. In fact, it just stopped right there. So we actually are going to say that this limit does not exist. Because for the limit to exist, the left side limit and the right side limit must equal each other. But there is no left side limit as x approaches negative 6. Okay? No left limit. All right, limit as x approaches 1. This is going to be part E. We're approaching 1 right here. So as we're approaching 1, again, notice it's not specifically left or right, so we need to have both in mind. They need to equal this. They need to approach the same y value. So as I approach 1 from the left and the right, notice that the y values are getting closer and closer to 3. Okay, now let's look at some function values. What is the exact function value at 1? So looking specifically exactly what's happening at 1, well, we can see that around 1, the function values are approaching 3. But exactly at 1, there's a hole right here, and the actual function value is down here at positive 1. So f of 1 is equal to 1. Let's look at f of 2. So here's the x value of 2. If we look at the left side of 2 and the right side of 2, we can see the limit doesn't exist, but the actual function value is right here at positive 2. That's where that little closed-in circle is. So f of 2 is equal to 2. And the last part here, the limit as x approaches 2. Well, again, we just saw this. If I'm looking at 2, if I'm approaching 2 from the left and the right-hand side, as we approach 2 from the left, we can see the y values are getting closer to 0. But if you approach 2 from the right, the y value is getting really close to 2. So since the left and the right side limits don't match each other as x approaches 2, they're not going to the same value, that limit does not exist. Okay, you have a Socrative to try. Make sure that you check eClass for that Socrative information. If you have any questions, please don't hesitate to send me a remind message or send me an email. I'd be happy to help you out. And if you have any other questions after that, we can, of course, clarify those on Monday. Hope you all have a great weekend. Try those Socrative problems, see how you do, and we'll touch base again on Monday.